Okay, presuming everyone can hear me, I'm gonna just give people a little bit more time so that I can let them into the room. I know it's 8. I'm just gonna wait till like 2 or 3 minutes past 8 because there's a waiting room and I have to let people in from the waiting room. Toby, can you look at the waiting room and just keep admitting people as they come in and I'll start. Okay, let's go. The waiting room is in the managed participants. Right. Okay, let's get started. Toby should be managing the waiting room. So if you're in there for a minute, don't worry about it, you'll get in. Okay, so the topic for today's photoelectric effect, I'll make announcements about the quiz in a minute, but I want to focus on that picture for a brief second. So that's Einstein, and obviously nothing moves faster than the speed of light, that being one of the postulates of the special theory of relativity. It's something that Einstein is known for. What Einstein actually got his Nobel Prize for was the explanation for the photoelectric effect, hence that tongue-in-cheek slide up front. Okay, now let's do a couple of Oops, quick announcements. There's a slide in here about the quizzes. Let me discuss the quizzes first. You'll get an announcement about the quizzes later today. There will be 3 quizzes in all that count for credit. There is 1 practice quiz that will be this Friday in Sapling. The link will be available in Sapling and in Blackboard. Now, when I say Friday, the quiz is actually timed any time between 8 a.m. and 11 p.m. You can take the quiz at any time during that time slot. However, once you start taking the quiz, you have 30 minutes to complete it. It is a bunch of multiple choice questions and one or two numeric answers. But this one is for practice. So this first quiz is on series and parallel circuits. And the idea is study up on series and parallel circuits. It's one topic it was at the end of the first exam. So take this quiz as a test on how to take an online exam. Okay, you'll need so I'm allowing you to use your notes and the textbook and the lecture slides. So all of that is valid resources. Non-valid resources would be Googling the questions on the internet. Asking your siblings for the answer. I mean, siblings have their uses. That is not one of them. Okay, so I'm trusting you guys not to use resources that you are not allowed to use. Just, take the quiz as it's meant to be, just to check on what you guys know at this point, and how much you can express. Okay, so that's the practice quiz this Friday. Starting next week, all the quizzes will be on Wednesdays. There will be 1 quiz a week. The topics for the quiz are pretty much chapters. So the first actual quiz that will count will be on next Wednesday, and that will be on chapter 23. That is wave optics, right? And the following week will be another quiz that will be on ray optics, and the following week will be the third and last quiz, which will be on this stuff, chapter 26. Okay, now. Someone asked if it's timed from the point that you started. Yes, it is timed from the point you started. When you open the quiz, it will tell you have 30 minutes to do it, right? You can skip around various questions in the quiz. It's not forcing an order, but you only get 30 minutes to actually do the quiz. So make sure you have the time to sit and do that quiz when you attempt to do it. Okay. I will answer more questions about quizzes if you have them on Friday when you're taking the actual makeup quiz, the actual practice quiz, and presumably we'll work out all the kinks then. Okay, let's get back to physics. So where we left off on Monday was the photon picture of light. So the photon picture of light says that light is transmitted as a stream of photons. And we can think of these photons as little packets of energy. And the energy of any individual photon, right, is given by E equals HF. And all photons, because they are packets of energy and light, they all travel with the same speed. They travel with the speed of light in vacuum. Right? So when light is traveling in vacuum, it's traveling with that speed. So what we're saying is we can think of light as these little packets of energy, right? We can think of light as these little packets of energy which are actually capable of bouncing off of stuff, right? Just like particles would. Okay, so particles have what we call momentum, right? I mean, yes, they have mass, right? But the motion of a particle, the amount of motion in a system is its momentum, right? From the definition of momentum. And particles have momentum. So the idea here is that light, when treated as a photon, has momentum. It is capable of hitting other particles and bouncing off of them and transferring energy in that bounce, right? Just like an actual particle would. Meanwhile, light is also a wave, right? Light is also thought of as a wave. So our big question today, hopefully by the end of it, is going to be to answer, when do we think of light as a particle and when do we think of light as a wave, right? Because it is both, okay? the dual nature is essentially saying that it will behave like a particle in some instances and it will behave like a wave in some instances. So now, of course, from physics points of view, one needs to be able to answer in what situations does it behave like a particle and in what situations does it behave like a wave. Okay, so as we move forward, right, this is our story so far. We're thinking of light in the photon picture as particles which have momentum and energy, and in the wave picture as an electromagnetic wave. The energy in an electromagnetic wave, if you remember, is stored in the amplitude of the wave. Okay. So in this, h of course is Planck's constant, and if you notice that number is tiny, right? So the energy of a single photon when measured in joules, right, is generally a very, very small number, which is why typically we use something like electron volts as our units for energy. But remember, SI unit is still joules. So if you're using something like this equation with H in SI units, make sure F is in hertz, and that will give you E in joules. Okay. Oh, right. This was the slide about the quizzes. Sorry, my order in the slides is messed up. So those are the dates for the actual quizzes and the practice quiz. This presentation will be uploaded later today. Okay. Now, the photoelectric effect. So what Einstein actually got his Nobel Prize for was what's called the photoelectric effect, the explanation of the photoelectric effect. The effect itself was known for a really long time. Now, the effect is actually fairly straightforward to understand in a sense. It's basically saying that when light hits a metal, right, light has energy. Some of that energy can be transferred to electrons in that metal, and those electrons can be ejected. Okay. So let's just go back to ejecting an electron from a metal for a second, right? A metal is electrically neutral, right? Any metal, in general, electrically neutral. It has the same number of protons and electrons, right? So net charge is zero, essentially. In a metal, you can think of the electrons as being free to move around within the metal, right? They're not bound to the atom itself. It's kind of like a sea of floating electrons with these fixed atomic centers, right? However, it's free to move around within the surface of the metal, right? Removing the electron from the surface of the metal actually implies you're ionizing it, because now you're fighting the attraction between the electrons and the positive charge substrates, right? Like whatever the rest of the metal is. So the electrons are held to the metal by electrostatic attraction to the nuclei, right? Just like in any atom. Okay, so if you can take energy and give it to that electron will start moving faster. It will get more energy, right? And at some point, it should get enough energy to be able to leave the metal. So at that point, you have removed an electron from the metal using light, right? So you've ionized it. Okay. So that is the photoelectric effect. The photoelectric effect is essentially photo, that's the light part, and electric, that's the electric part. Electrons, that's the electric part. Light hitting the surface of a metal can eject electrons from that surface, right? This effect is called the photoelectric effect. Okay. Now, in terms of explaining this effect, right? You have two possible explanations depending on which theory of light should apply, right? The prevailing theory of light at this point in time, before Einstein came along and explained it, was the light is a wave. Okay, so I'm going to switch you guys out to my screen in a sec. Okay, so what we're saying is this is a metal, right? And light, right? Some photon, so this is light, right? Is incident on this metal, and this ejects electrons, right? So this electron was originally in the metal. It absorbed the energy, it got some energy, enough energy to overcome its binding attraction to the metal surface, and it ejects, it leaves, right? It gets enough energy to eject itself from the metal. Okay, this is the effect. This is the photoelectric effect. Now, according to the wave theory of light, right, this should be a relatively simple explanation. Right? You have light is a wave. So if I have light at some particular frequency, this is time, this is the electric field, right? So the magnetic field would be this way, in and out of the board, the beam is traveling in that direction, right? And this guy, the amplitude, determines the energy, right? So when this photon, right, the energy of this, in this photon is absorbed in this wave, is absorbed by this electron, it is ejected, right? Great. So one might think, what's the issue there, right? But that's one explanation. Okay, that is the wave theory explanation. Now remember, let's look at one thing about the wave theory explanation. In the wave theory explanation, there is no relation between frequency and energy, right? The energy is associated with purely the amplitude of the wave. Okay, so at any frequency, let's say at some frequency, let's say we're in the red, right? So F red. Okay. At some frequency, F red, I can have any amplitude I want. That means I can have a beam of red light, right, with any energy that I want just by changing the amplitude of the beam, right? So in terms of this, right, even if I have like a really low intensity beam, right? So low intensity implies that the amplitude is very, very low. Right? So that small amplitude implies small intensity, low amount of power per unit area per unit time. Okay. So even if I hit this surface with a reasonably low intensity, right? If I hit it for long enough, so I'm dumping energy on it, right? If I keep dumping energy, at some point I will dump enough energy into this metal to remove this electron, right? Because the electron needs a certain amount of energy to be able to leave that metal. Okay, so according to the wave theory of light, right, any frequency, right, even at a low intensity, will be able to eject electrons if it's left on for long enough, right? And if I increase the intensity, then it will take less time for the electrons to get the energy and eject, right? But there is no relation in this theory between frequency and energy. Okay, that is the important point. Okay, the point here, according to the wave theory, this is your takeaway. According to your wave theory, any frequency, right, of light should be capable of ejecting an electron from the surface of this metal, right? Because I can vary the intensity of the beam, and that changes the amplitude of the wave. Okay, that is the wave theory. That's the wave theory prediction. That any frequency, if it has enough, if you have enough energy in the beam, it will be able to eject electrons. Okay, now let's look at the other theory. The wave. This was the wave picture, right? The photon picture is a little different. In the photon picture, the photon is carrying a certain amount of energy, E, right, which is related to its frequency, right? So in the photon picture of light, this beam of light is made up of n photons of that frequency, right? So this is a beam of red light. It consists of n photons of red light. The energy of each photon of red light is just that much, right? The total energy in this beam is the total number of photons in the beam times the number times the energy of one single photon. Okay. Now, so in this picture, right, the interaction between the electron and a photon is like two particles bumping each other, right? So in this process, if the photon is absorbed, right, the energy of that photon is given to the electron. Okay. So here's the thing. The energy of the photon is given to the electron, right? So let's say the electron requires some amount of energy, which I'm going to call W, to be ejected from the surface of the metal, right? However, if the energy of this photon, right, the HFR, is less than W, right, then in this interaction, in this absorption, the electron absorbs the photon. Yes, great, but it is not enough energy to eject, right? So it won't eject. Okay, according to this, right, if the energy of a single photon, right, is less than the energy required to eject the electron, it doesn't matter how many photons I hit it with, I won't eject anything, right? So it predicts that there exists a certain frequency, right? Of course, I can increase the energy of the photon by increasing its frequency, right? In this picture. So according to this picture, there exists some frequency, or there must exist some frequency, right, for that photon, where it doesn't have enough energy to eject the electron. And for all frequencies below that frequency, it will not eject, right? There is some minimum threshold frequency which corresponds to a minimum threshold energy, right? In order to eject an electron from the surface of a metal. Okay, so those are two predictions, right? And they're two fairly different predictions. One says, according to the wave theory, of course, it says that any frequency of light, right? Any frequency should be capable of ejecting an electron. The other says that no, any frequency is not capable of ejecting an electron. You have to be above a certain threshold frequency, and that threshold frequency is set by how much energy is required to remove that first electron from that metal, right? That photon has to have at least that much energy, okay? Above that energy, and we'll discuss that in a minute, the photon should have at least that much energy, but then what happens if you have a photon that has significantly more energy than is required to eject, right? That's our next question. Okay, but you have these two different predictions, okay? And obviously, since Einstein got a Nobel Prize for the explanation of the photoelectric effect using photons, the photon picture was actually the one that's correct, right? Experimentally, people found that yes, there exists a cutoff frequency, okay? So there exists a frequency below which no electrons are ejected from the surface of the metal, okay? Yes, Jordan asks if it depends on the metal. Right, it does. The amount of energy required to remove an electron from the surface of a metal depends on the metal itself. Right, different metals require different amounts of energy to eject that first electron. Okay, so if you take a certain metal and you plot, right, this is telling you the kinetic energy of the most ejected electron. We'll come to that later. But remember, in order for there to be a kinetic energy of the most energetic electron, there needs to be an ejected electron, right? And over here, if you see below this F0, right, what we're calling F0, below F0, no electrons are emitted, right? This is just a back projection. So there exists a cutoff frequency, right? So the photon needs to have at least that frequency in order to eject the electron from the metal. And then when you start increasing the frequency of the photon, the ejected electron starts moving faster. And we'll discuss that in a quick second. But here, this very fact right here, that there exists a cutoff frequency below which no electrons can be ejected from the surface of the metal, proves that light behaves like a photon, right? That light is transmitted as a photon. It is absorbed as a photon, right? It is, its amplitude is not independent of its frequency, right? Once you have a certain frequency, a certain color, the energy at that color is coming in discrete packets, right? And each of those packets is what we call a photon, and it has an energy of h times f, where f is its frequency. Okay, so by the way, I'm going to write something on the board, so I'm going to stop share for a quick second. Scott, I'll answer that in a sec. E is HF, right? So F, so remember, right? Speed of light is wavelength times frequency. So I can rewrite this as E is HC over lambda. Okay. So someone asked how does this, the explanation of the photoelectric effect prove that light behaves like a photon? Remember, the difference is the wave theory predicts that since frequency has nothing to do with energy, right? I can have any energy in a wave by changing its amplitude at any frequency, okay? So according to the wave theory, any frequency of light, right? If I have a high enough intensity, right? So I have enough amplitude in that wave, so to speak, right? At any frequency, I will be able to eject electrons. What the actual experiment shows, right? The actual experiment, when you take a metal and you radiate with low frequency light, nothing comes out. Okay, so the wave theory is not accurately predicting what is going on. The particle theory, on the other hand, right, or the photon picture, right, is basically saying that you need, the electron needs a certain amount of energy. The photon needs to have that much energy to eject it, right? And the energy of a photon depends on its frequency, right? So below a certain frequency, it won't have enough energy, so nothing will be ejected. Above a certain frequency, it does have the energy, so when it's absorbed, stuff is ejected, right? So that is what it's proving. Like, it's proving the photon picture, as in the explanation from the photon picture fits the experimental observations, that there exists a cutoff frequency below which no electrons are ejected, no matter what the intensity of light. Okay. Now let's go back to this. Okay, so now let's discuss what we mean by kinetic energy of this ejected electron. So this is an animation in a sense. You have a photon, which you can think of as a fundamental particle of light. The energy is hf. H is a really small number. The idea is, if the photon doesn't have a high enough frequency, which means it doesn't have enough energy, it can't dislodge an electron. However, if it does have enough energy, it is absorbed and it emits an electron. Now, what happens when it has more energy than is required, right? So let's say it requires 2 eV to eject the electron, right? And the photon had 3 eV. What happened to that one extra eV, right? That is our current question. And the answer is that goes into the kinetic energy of the ejected electron. So the way to think about this is really like posting bail, okay? Let's say that something is incarcerated, right? And bail is posted at $10. Okay, so what we're saying here is that bail amount, right, is the equivalent of the amount of energy needed by the electron to leave the metal, right? So if we say bail is set at $10, we're saying that the energy needed to get out of jail is $10. So this good Samaritan comes along, and that's the photon, right? If the photon has $5, right, it doesn't matter. He's not going to be able to get you out, right? Which is saying that if the threshold, if the energy of the photon, HF, is lower than the energy required to eject the electron won't be ejected. Okay, and the energy of the photon is HF. So a higher energy photon is a higher frequency photon. Okay, so now let's get a higher frequency photon. If I get a photon that has, let's say, $11, right? Great. So he gives me the $11 and I use $10 to get out of jail, and I have $1 for the cab ride home. Okay. On the other hand, if a photon comes along that has $20 and gives me the $20, I use the $10, and the remaining $10 is what I have left over for the cab ride. Okay. So what we're saying is that this leaving electron, right, the electron that is ejected from the metal, has kinetic energy, right? It has a mass, it has a speed, so it has a KE of one half mv squared, right? That amount of energy is that leftover energy, right? How much energy it's ejected with, the ejected kinetic energy of that photon, is that difference in energy between the high energy photon that ejected it and the actual amount of energy that was needed to eject it. Okay, so as we start using higher and higher energy photons, right, when they are absorbed, the electron coming out is moving faster and faster, right? So what you're changing is the speed with which the electron is coming out. You're not changing the number of electrons that are ejected. The number of electrons that are ejected is dependent purely on the number of photons that are incident, right? And the number of photons that are incident doesn't have much to do with the energy of a single photon. Okay. Right, let's put some math to this. So the work function is the amount of energy that is required to remove an electron from the surface of a metal, right? And it is defined as the amount of energy required to remove the electron from the surface of a neutral metal, right? The reason being, because once it's neutral, when it's neutral, it requires a certain amount of energy to remove the first electron, right? But the next electron in there is more tightly held because you have removed an electron, making that thing positively charged. Yes, someone asked if one electron is ejected per photon. Correct, that is the picture that this is talking about. This is an interaction of a particle like photon and the particle electron. So it is a particle-particle interaction. So if I want to eject 10 electrons, I need 10 photons to interact with 10 electrons. Okay. The work function itself is that amount of energy, that minimum amount of energy that is needed to eject that first electron from the metal. Okay, so the work function depends purely on the metal. It is the Bale amount set by your crime, right? Essentially saying it depends on the metal. And so this is potassium, right? So this is the photoelectric effect on potassium. So potassium has a work function of 2 electron volts, okay? So if I send in a 700 nanometer photon, so this is a beam of red light, right? Each photon at 700 nanometers contains 1.77 electron volts of energy, right? So this energy is less than the energy needed to eject the electron. So nothing will be ejected, okay? Now, green light comes along. So remember, I'm looking for higher frequency, right? In order to eject, I need more energy. So I'm going towards higher frequencies. Green is the higher frequency than red, right? And this wavelength of green has an energy of 2.25 electron volts, right? Which is more than the energy needed to eject the electron. So you have 0.25 eV left over. That 0.25 eV is the kinetic energy carried away by the ejected electron. Now, if you use an even higher frequency photon, so blue, right? There's actually violet, 400 nanometers, 3.1 eV, right? Yes, more than enough to eject, and you're left with 1.1 eV, right? So this ejected electron now has 1.1 eV of actual energy, right? That's its leftover Bale money. So it's moving faster, okay? So the point here is you still require one photon, right, to get one electron, okay? As you keep increasing the energy of the photon, the kinetic energy of the ejected electron keeps increasing, okay? If you ever want to increase the number of ejected electrons, you have to actually increase the number of incident photons, okay? Which means you have to change the intensity of the beam, the amount of energy in that beam. Okay. So this is essentially a summary of the explanations for photoelectric effect. This is an example of a use for photoelectric effect. This is fibrinogen on a substrate. The reason for this image is it was actually collected using photo emission electron microscopy, or photoelectron emission microscopy. Essentially, you're hitting the substrate and the fibrinogen with light, and the substrate and the fibrinogen eject different amounts of electrons for the same incident light. So your contrast is generated from the fact that one is ejecting more electrons than the other. Okay, so that's how you can generate contrast. Other uses of photoelectric effect: solar cells, Einstein's Nobel, etc. Okay, I know you've been waiting for clicker questions. Okay, let's analyze what this question is saying, right? It's saying that the cutoff frequency, right, is greater for metal B than it is for metal A. Now, First off, cutoff frequency is the frequency below which no photons are ejected, right? So the cutoff frequency corresponds to that work function. Okay, I'm gonna sneak a look. Very good. The higher work function corresponds to the higher cutoff frequency, right? You need the work function in terms of the amount of energy of the photon as the minimum to be ejected, right? The energy of the photon is HF. The higher the value of the work function W, the higher the value of the cutoff frequency. Okay, so click something and good. Okay, so that's metal B. Now do this one. Now over here, it's actually this form. So it's giving you that phi0, right? That's the symbol they're using for the work function. Now I want you to look at that description of the work function, right? So it's saying that the work function is, I'm going to stop the share for a quick second so you can see my board. The work function is the amount of energy required to eject a single electron. So if this is the cutoff frequency, the minimum energy required by the photon is the work function. So the photon must have a cutoff frequency Fc, right? Which is related to the work function this way, right? Any frequency, any photon with frequency less than this won't eject, more than this will eject. Okay. Now let's rewrite this. Fc, the cutoff frequency, is Hc over lambda, right? Where wavelength is the cutoff wavelength. Okay, so remember, frequency and wavelength are inverse, right? C is F lambda, which means as F, and C is constant, right? So as F goes up, lambda goes down, right? So in terms of wavelength, if we're talking of a higher energy photon, we're talking of a shorter wavelength photon. Okay, so yeah, I'll do that in 1 second. So essentially what we're saying here is that this is another way to write the work function, and any wavelength shorter than this will eject, and any wavelength longer than this will not eject, right? Because a shorter wavelength has more energy, a larger wavelength has less energy. Okay. Right, that should allow you guys to see the options. So option A is the emitted electrons are more energetic. Option B is emitted electrons are less energetic. Option C is fewer electrons are emitted in a given time. And option D is no electrons are emitted in a given time. Okay. The answer, of course, sorry, I didn't mean to go that far forward, is that no electrons are emitted. And the reason for it is this. So what this is telling you is that the work function is given in this weird form, Hc over some number in nanometers, right? So what I want you to realize is when it's given in that form, right? When it's given in this form, this number, right, is the cutoff wavelength, right? It is this lambda c. So any wavelength longer than this will not eject, and any wavelength shorter than this will eject, right? Does that make sense? Right, because it's basically telling you the work function is written in that form. Okay, and that is what this question is telling you. So red light has a wavelength of about 700, which is of course longer than 500. Right? So red light will not be capable of emitting electrons in this case. Okay, I'm going to close that question and move on to the next one. Now, in this case, the metal surface is struck with light of 400 nanometers, okay, releasing a stream of electrons. If the 400 nanometer light is replaced by light of 300 nanometers, what is the result? So first off, understand what's happening. Has the energy of the light that is hitting this surface increased or decreased, the energy of that photon, right? So you went from a lambda equals 400 nanometers, which was releasing electrons, right, to a lambda equals 300 nanometers. So the first question, right, Patrick's saying the energy went up. The first question is the 300 nanometer photon more or less energetic than the 400 nanometer photon? And the answer is, it's a shorter wavelength, so a higher frequency. So it is more energetic, right? The 300 nanometer photon has more energy than the 400 nanometer photon. Okay, so the question now becomes, obviously, if the lower energy photon is emitting, the higher energy photon will emit, right? So there will be electrons emitted. The question now becomes, what is true about these electrons that are emitted? I am now hitting it with more energy. Is that energy going into releasing more electrons, or is that energy going into increasing the energy of the ejected electron? Remember, we're still treating this, right? The photoelectric effect is the treatment as, you're treating this effect as two things bouncing off of each other, right? The only way to get more electrons to eject is to hit it with more photons. In this case, you're not hitting it with more photons, you're actually hitting it with fewer photons, right? Because 300 nanometers, the light is more energetic, so you need fewer photons to get to the same intensity. Very good, right? The emitted electrons are more energetic, right? So the extra energy between the 300 nanometer photon and the 400 nanometer photon went into the energy of the emitted electron. Okay. So in this question, we're actually changing the intensity without changing the wavelength. So I'm getting a more intense beam at the same color, right? So since that color, right, released electrons, a more intense beam at that same frequency will still release electrons. Now, by saying we're increasing the intensity of the beam, what we're actually changing, of course, is the number of photons in the beam. Remember, intensity is the total energy in the beam, right? So if I have a beam of 400 nanometer photons, right, then the total energy in that beam is the total number of 400 nanometer photons I have multiplied by the energy of a single 400 nanometer photon, right? So the way you increase intensity is you put more photons. So now if I have more photons incident on this metal surface, what should happen? Remember, each photon is capable of ejecting an electron in this case, and I am now just hitting it with more photons. So click something, please. Very good. Okay, I'm going to close this. So you eject more electrons in the same time interval. And one last question. Actually, sorry, no one answered that. I'm going to actually close out of this before I send it out. Yeah, there you should get it now. So in this question, you're saying a photocell is illuminated with light with a frequency above the cutoff frequency. So obviously, electrons will be ejected. So in order to answer this question, right, what you have to remember is current. What is current? It is charge per unit time, right? So in order to get an increase in current, right, or the magnitude of current, like how much current is generated, depends on how many electrons are ejected, right? The more the number of electrons ejected, the larger Q is, right? So the larger the amount of photocurrent. So this question is essentially asking you, how do I increase the number of electrons that are ejected, right? That's what the current in this system becomes. This is very similar to the question you just answered, right? When we're talking about the magnitude of the current, what we're literally talking about is the number of ejected electrons, right? So out of the options given in this question, which of these options will change the number of ejected electrons? How do I change the number of ejected electrons? Very good. Okay, click something. No, you're not actually ejecting that many. It's Q over T, yes, but how fast they're moving is not the same as how fast they're ejected, how many they're ejected per unit time. How fast a charge moves isn't, the speed of the charge isn't current. Hopefully that makes sense. Right? Current is not how fast charge is moving. Current is how much charge is moving, like what quantity of charge is moving per unit time. Okay. Very good. Intensity, right? That's the way you increase the number of electrons being emitted. Okay, good. Now, we started this by saying light has both a wave nature and a particle nature, right? The particle nature is the photon. The wave nature is the electromagnetic wave picture. Both pictures are true, okay? So the question becomes, in what case do I use the wave picture? In what case do I use the particle picture? That's one question. The second question is, does this extend to other stuff apart from light? And the answer to both questions, well, the answer to the second question is yes, it does. It extends to all matter. Okay. Photons. The energy of a photon is HF, right? So it depends on the frequency of the photon. Now, we've been treating this photon, or at least I keep saying that we need to treat this photon as a particle, right? And obviously a photon has no mass, right? A photon has no rest mass, so to speak. It is a packet of energy, that much energy moving at the speed of light, right? It has, however, got a momentum, right? The momentum of a photon is given by this expression. So P, if you remember, right? Classically from last semester, mv, right? For a particle of mass m with speed v, I can say the momentum is mv, right? Okay. Obviously, with a photon, I can't say that because m is 0. Okay. But v is c. Okay. So this is the relation of momentum of a photon. It is inversely related to its wavelength, and h is Planck's constant, right? So h is 6.6 times 10 to the minus 34. So what this is telling you is that every photon of some wavelength, lambda, right, has a certain amount of momentum, right? And remember, lambda and frequency are inversely related, right? So this would be hf over c. correct? So in terms of frequency, the momentum of a photon increases with its frequency. So higher frequency photons have more momentum than lower frequency photons. Okay, so now we're talking about, standard examples of like low momentum and high momentum. If you have two things moving at the same speed, right? If we go back to last semester, my standard example was little kid and a bigger little kid, both running at you with the same speed. The bigger little kid has the larger momentum. When they bump into you, they have more chance of doing damage. Okay. So this is its particle nature. This is its wave nature. So there is a momentum associated with its wave nature. Okay, this expression for momentum of a photon, someone called De Broglie said that, okay, what about particles, right? Okay, we're saying light does this, right? We're saying photon does this. It has a certain momentum and a certain wavelength. So a photon of a certain wavelength lambda has a momentum p, and it interacts with other particles based on this momentum p. Okay. De Broglie said, why not? What about particles? Particles have momentum, right? So I have a particle moving with speed v, it has momentum mv, right? Is there a wave nature associated with particles? Okay, and that is the dual nature of matter. So it's not just dual nature of light, there is dual nature of matter. All matter has wave-like properties. The same equation, right, can be written as lambda is h over p, right? So if we're talking about some particle of mass m moving with speed v, it has a wavelength associated with it. Okay, so that means it has wave-like properties. Okay, for most ordinary objects, right, if you look at the numerator and denominator in that expression, right, lambda is very, very small. Right, even for like an ordinary like atom, right, moving at some reasonable speed, this number comes out to be ridiculously small because this number is 10 to the minus 34. Okay, so for stuff like us, right, and tennis balls, our momentum is huge. So our corresponding wavelength, right, is very, very small. And now let's be clear on what I mean by corresponding wavelength. So in the very beginning, we said, at what point do I consider wave nature and at what point do I consider particle nature, right? So go back to what the wave nature meant. Wave nature meant that light or particles, according to this, is behaving like a wave, right? That means as it passes through openings, it spreads out, right? Diffracts. As it gets to different places, it interferes, right? So waves produce interference patterns. Okay, now in order for this to happen, these openings, right, these edges that it's bending through, the size of the slit, so to speak, has to be of the order of the wavelength, right? This is why going back to somewhere in the beginning of the semester or halfway through, we said light doesn't bend through doors, right? The opening is too big. Okay, so that's why you can't see around a corner. Like the light doesn't bend around the corner, so you can't see a person around the corner, but you can hear them. Sound waves are long, so they will bend, right? So the amount of bending is proportional to the wavelength of light or the wavelength of the particle and the size of the opening. They have to be of the same size, right? So for a tennis ball moving at an ordinary speed, the wavelength comes out to be 10 to the minus 31 meters. What that means is, in order to see a tennis ball interfere or diffract or behave like a wave, I need slits which are of the order of 10 to the minus 30 meters, right? Nothing is that small. Okay, so we do not see the wave nature of ordinary large objects simply because they have a large momentum. Okay. So we see their particle nature, right? Because of their large momentum, we don't see them interfere and diffract. On the other hand, subatomic particles. So the smallest particle we know of, for example, is an electron, right? So the question, the lowest mass, right? At least the ones that we can easily set up in a lab. we can generate electrons using an electron gun. Just eject electrons. Electrons have very, very small mass, right? So if they're moving relatively slowly, mv is a small number, okay? Which means this lambda becomes a relatively larger number. It's relatively larger, it's still pretty small. The wavelength of an electron. Okay, so before we actually see some pictures on that, I want you to answer this. The electron and proton have the same speed. Which one has the longer wavelength? Remember, we're saying lambda is h over p, right? So p is the momentum. Sorry, I'm going a little bit over time. But click something. Remember, the greater the momentum, the shorter the wavelength, right? They both have the same speed. So the one with the larger mass has the larger momentum. Okay, I'm gonna close this. Let's see where you guys are at. Mostly right. Yes, sorry, no, mostly wrong. The one that has the larger momentum has the smaller wavelength, right? P is h over lambda, right? So lambda is inversely proportional to momentum. So the larger momentum has the smaller wavelength. Yes, that is correct. Okay. Electrons actually do have a larger wavelength, and electrons interfere, which is this. So if you take a bunch of electrons and you do a double slit experiment, they behave like this. These are the results of a double slit experiment on electrons, right? And you can see interference lines, right? So electrons interfere, right? Unlike, not like particles, as long as these slits are of the order of the wavelength. Okay, so I'm going to let you guys go. Remember, you'll have emails from me outlining the quizzes and the homeworks and deadlines coming up. I'll summarize all of it and send out an email later today. Stay safe, have fun.